Hi everybody, welcome back. So before I disclose what our next project is, I just want to tell you that I'm pretty excited about it. It's something I've never worked on before, which is always fun, and it'll be really interesting to see how this thing works. Now, I'm going to start this one out we'll do a quick test on it before we do any work on it at all, and then we're going to do a little bit of theory with the schematics in this part. This will be part one. And I had to order some parts for it because it's going to need just some updating, refurbishment, whatever you want to call it, for restoration. It's in really good shape. You'll see that, and it probably works. I don't know. We're going to find that out together too. But the more I looked at the schematics on this, the more interesting it got. And I think there's going to be some quirks that these things are going to have inherently, and we'll see if we can do something to make it a little more reliable and still maintain or retain all of the original charm that this thing had in its design. So they're not really common, although you can get them out there, but this is the first one I've ever had on the bench, and it'll be the first time I've ever heard one, so pretty exciting. So without further ado, let's take a look at what we have. Okay, so what we have is a Pioneer model M-22 power amplifier. They made two different versions that look the same but are very, very different. This one is the M-22, the other one is the M-25. They both kind of have this similar layout, but the big difference is this one is all Class A, and the other one, the M-25, is a Class AB. Big difference in how they perform. This one is supposed to have a really, classic kind of warm sound, similar to how a tube amp. I'm expecting this to sound somewhat like the Marantz Model 15, and I did a video series on that. So maybe it'll be kind of like that, I'm not sure, but I'm really excited to hear it. The M25, and this thing is as big as it is, it's heavy. It weighs like 50 pounds almost. And for how heavy it is and how big it is, two big transformers, four 33,000 microfarad capacitors, and all these huge heat sinks, and this is a 30 watt per channel amplifier. Talk about really, really inefficient. So this is the gas hog of amplifiers. The M25 is about the same size, and it's rated at 125 watts per channel, but it's Class AB. So why would you do that? By the way, this thing dissipates almost as much power, a lot more power in standby than that M25 will dissipate, because Class A, the amplifier is running pretty much at full power even when there's no signal going through it. That's kind of how they work. And we're going to see that. We'll do a little experiment. We'll hook the kilowatt up, and we'll actually watch when the amplifier has no load going or no signal going through it versus when we have full signal, how much the current draw from your AC mains is going to be. I'm going to guess that if this is a true Class A, not going to be much difference. And as a result, these get very, very hot. So of course you're going to have a lot of thermal problems with thermal tracking of the semiconductors. You're probably going to have capacitors that have had a lot of heat applied to them over the years, depending how much this thing's been used. And this is all stuff we're going to have to find out as we go along. There's one piece missing to this, and it really bums me out. This thing has a removable tag that has the model name and Pioneer logo and all that on it, and it's metal, it's really high quality, and it has two screws that holds it, and there's different places around the amp that you can mount it, so that if this is facing forward, you can put the name tag on the front. If you have the amp facing the other direction, like you make this the rear of the amp, you can move that tag over to the front. It's really cool. This was kind of their really boutique high-end series. I have a matching preamp to go with it as well, and we're going to do a video on that, and that comes later. But so far, I haven't done anything with this. Let's power it up. Let's see how it works and if it works, And if the relays come in and everything, I say let's put a signal through it and see if we have some sound. So first things first, let's just see if it powers up. I have some rather large light bulbs connected. You can even imagine if this one, there's two versions of this amp. One of them I heard has a soft start circuit for the caps. One of them does not. I don't know if that's true or not, but I've read that somewhere. So I don't know. I think this one will have, I'm hoping this one has the soft start circuit. If not, that bulb is going to get really bright when this thing first powers on as these caps charge up. So let's turn it on and see. Hopefully the bulbs won't stay on constantly, and I'm just going to do this big one right here, 300 watt. Here we go. And we got nothing. Well, that is because I'm on direct. That's not good. All right, now we're on current limit. There it goes. And you can see it came through the soft start. I heard the first click. I don't hear a second click, and you look how bright that is. And I believe that is because this amp idles at such a high current that it's dragging everything down right now. You're not getting enough current to activate the protect circuit. So let's add another bulb. And it clicked. I heard it. Did you hear that? So look how much power this thing is dissipating just at idle. That is not a shorted transistor. If it was a shorted transistor, those would be full brightness. But it took two of those bulbs. It took a 300 watt and a 110 watt bulb in parallel to deliver enough current to get the voltage enough to where it will release the protect relays. And this does have a soft start. So far, I think this is okay. And I think we should be all right to go on to just direct power. And this has a fuse in it as well. So, all right. Let's go for it. Okay, you can see I have this plugged directly into the mains, and I'm going to go up here, and we're going to just focus in on the kilowatt, which is, it's sideways, so we'll just have to put up with that. I need to order another one of these. They make these now with little backlights in them, and that would be awesome to see. So maybe I'll get one of those eventually. So let's turn the power on. And you can see right now we're idling at 232 watts, and it's creeping up. 230 watts of dissipated power. I don't know if you could see that on this thing or not. Let's see if there. 239 watts. Look at that. And there is some shutter roll on the camera, I see. 240 watts. I don't have speakers connected, nothing. That is crazy, isn't it? So, and the thing is, I have a feeling when we drive this amp, put a signal into it, that's not really going to change a whole lot. We'll do a little experiment. We'll look at that. Okay, let's now look at if there's any offset on the speaker terminals. I heard the relays click, so I'm assuming there won't be. And you can see right there, I'll go to millivolts. 1 millivolt, that's great. How about this side? Ooh, that one's got negative 33 millivolts. That's still not bad though. 33 millivolts is not going to do anything to your speakers. And to my understanding, these don't really hit their stride until and you can see this is drifting up a little bit. These don't really regulate until they get up to operating temperature. And I can feel these heat sinks already warming up. I mean, they're above room temperature now. They're not cold, but they're not warm yet. But I can feel them just at or above room temperature. And the longer we wait, the warmer they're going to get. And apparently these are supposed to warm up for 10 minutes or so to stabilize before you even get the best sound quality out of them. So we'll have to remember that as well. So while this is all going on, let's connect some speakers and an audio source and try to get some sound through them. Okay, I have a signal source and some speakers connected. And what I'm going to do is I'm going to try to get some obnoxious YouTube safe music that's kind of bass heavy if I can find something. And I just want to really get this thing cranking up a little bit. And I'm going to focus the camera on the kilowatt. And we're just going to see as we turn the volume up on the amplifier if the current draw changes. You're probably going to see now in a Class AB amplifier, the louder you go, the more wattage you'll dissipate from the mains. And I have a feeling this is not going to do that, but we'll see. Okay, I should have something sufficiently obnoxious that we can listen to, and it is very bass heavy. And let's just see what happens when I crank it. And again, this amp is 30 watts per channel, so the most we're going to push into this system is theoretically 60 watts, but I can guarantee you that is really deceptive when you deal with these types of amplifiers. So let's start it up. I'll move the mic close to the speakers. Let's turn the volume up. Yeah, so that was compressing my chest. And if you notice, the wattage didn't move at all. And that's very characteristic of a Class A amplifier. So I think you can tell where we're going to go with this part one, is we're going to talk about what makes a Class A amplifier different than a Class AB, and why these are considered to be better sound quality to some. Not everybody will agree with that, but those who have worked with this type of product line, these Class A high-end amps, they'll tell you that they do sound really good. And they have a ton of headroom for their power rating. Again, why do you need 66,000 microfarads of capacitance for a 30-watt amplifier? I mean, these are dual power supply. We'll get a little more into that. So this thing works perfectly. I don't see any reason that I should have to do anything to it. And probably all that we're going to do is we're probably going to update the speaker protect relays so that they're not, kind of reduce any type of corrosion or anything that we might have on there. And I'm going to replace the electrolytic capacitors, because just that little short demonstration, and these things are already getting really warm. They're not burning my hand yet, but they will get really hot. I mean, 244 watts, that would mean, 120 watts per side. So yeah, you're dissipating 120 watts to get 30 watts out to your speakers. Gas hog. Okay, this has been playing for a while, which doesn't matter because this thing will get the same temperature if you're playing it or if you're not playing it, because again, it's Class A. So let's take a look down here, and you can see we're right around 123 degrees Fahrenheit. This thing's set to Fahrenheit. And let's look at the other side. I want to make sure that they're symmetrical. That gives you a little idea of what kind of idle current we have. Let me spin this around, hold on, without catching all my wires. And this one here, on this side, about the same, 123, 125. So this is really good because what this means is that both channels are tracking the same as far as idling goes, because they're both dissipating the same amount of heat. If one side was getting significantly hotter than the other, that would be a sign that something's not right with one of the channels. But they're both, it means this thing's in absolute perfect condition. I mean, I could just turn around and use this every day. The only thing I do notice, and I don't know if I can show it to you on the camera. Give me a second. So I'm not sure in the camera if you can see, but I can pretty clearly see this capacitor here is bulged at the one end a little bit. It doesn't appear to be leaking. I mean, it's got dust on it. It's a little bit dirty, but I don't see anything really bad other than that. But yeah, these caps probably have seen their fair share of heat. So I will replace those. And I had to order a few of them because there are some axial leaded capacitors that I don't keep in stock. And I want to get ones that operate at high temperature, at least 105 C or higher. This is starting to get super hot now, like uncomfortable to hold my hand on hot. And let's let's fire up the thermal camera and take another look at it. Okay, so you can now see the whole top of the heatsink is getting hot, and it's all about 126 degrees, 128, and it's climbing still. And the other channel, just looking at it real quick without moving the camera, it's identical. It's 126. So that's hot. That is quite hot. And it's just getting hotter a little, and it'll probably get up there a little bit more before it settles. And the issue is you're cooking the board, you're cooking all the components in there. So after enough time, you know, it'll eventually cause damage to some of these components. It's a miracle that I don't think this amp was used very much, to be honest. I don't think anybody listened to it very much because the boards, just looking through the grill in there, the openings for the air vents, I don't see any scorch marks on the boards yet or anything, and I really don't want that to happen. So we're going to get this thing cleaned up and do a couple mods to it to make it handle the heat a little better without changing the character of the amplifier, how it sounds. All right, we're going to now look, while I'm waiting for components to come in, and I'll finish up part one with this, we're going to look at some schematics and kind of try to figure out how this thing works. Okay, so let's get acclimated to the actual whole amplifier circuit. It's actually a pretty straightforward circuit after you look at it for a little bit. It's a little confusing at first, but it's really not that bad. First of all of these things are dual mono. So you have two power transformers, two bridge rectifiers, two of those sets of great big 33,000 microfarad capacitors. So everything's just 2 amps built on one chassis. You have left and right channels here, and that's like, this is the left amplifier, this is the right amplifier, this is a regulated power supply, and this is a regulated power supply. So there's 2 sets of power supplies for each of the 2 power supplies, if that makes sense. So this is the big 28 volt, plus and minus 28 volt supply. And that is what drives the output section. That's all it does. It drives the outputs. And then the regulated plus and minus 36 volt power supply, those actually are what drive the preamp section, you know, out in here. And we'll see that more closely when I have another kind of worked up schematic that I did. This is your protect circuit, and it works a lot like all the other ones. It has, there is an over temperature sense. So you see these 2 thermistors, And it's kind of interesting how they do this. So if you look at this thermistor, it starts out at a low ohm value, I believe. And what happens is if the heatsink gets too hot, this will change resistance very rapidly. It'll then change the voltage drop at this point right here, and it will eventually gate this SCR on. You see that right there? And I can zoom you in a little closer to see that. So you have this SCR, and once this is a set and forget, so once this trips, you actually have to turn the amplifier off and back on to get it to reset. And the whole idea is you have to wait until the heatsink cools back down before it will allow this to unlock, and not trip again when you turn it back on. And that's going to drop out your protect relay and so forth. It's just going to keep the thing from overloading. In addition, it has, your midpoint protect, meaning it's going to look, you have a feedback right here, and it's going to go back and go into here, and this is what's going to check to see if you have too much DC offset. If it gets beyond a certain point, plus or minus like a volt or something, again, it'll drop out the protect relay. In addition, there's an overcurrent circuit. Again, if you have something, it's kind of designed to trip when it sees something below a 4 ohm load. Again, you have an overcurrent situation, it'll trip the relay again. Another interesting thing is this resistor right here, and I'll show that a little more carefully or a little more closely in the other schematic that I have. But I just wanted to give you a general overview of what's going on in this thing. It's really not that complicated. These are pretty simple power supplies. This is an unregulated for the plus and minus 28, which is normal. These are your high current power supplies here. And then the low current power supplies, plus and minus 36 volts, one for each channel. This one's for the left, this one's for the right channel. And again, they provide the voltages for your input pair, your pre-driver and current mirror, your driver section and so forth. And then, this section here. And then the driver and output section is driven by the plus and minus 28 volt unregulated supply. So now let's look at the close-up shot. Okay, so I just took a cut of one of the channels and kind of photoshopped it a little bit. I just used MS Paint and kind of highlighted some of the circuit paths. So if you break it down, this front section is your input section, and you have a differential input pair, pretty common that you see in a lot of these amplifiers from this era. And this is a transistor package. So that means it's an oval shaped transistor case with 2 transistors inside. So it'll have like 5 pins, 1, 2, 3, 4, and 5 there where the collectors or the emitters are tied together. And they do that for thermal stability. So the 2 transistors will thermally couple to one another. And as the temperature changes, these will both change at the same rate. So that kind of helps with stability and to keep the offset from changing. In addition, this is kind of unique. You have this little offset protect circuit. So you have these 2 D4 and D5. And if you look at the service manual and look at the description of function, they talk a little bit how these are thermally matched diodes. I don't think they meant they matched them on a curve tracer. It's just that they're the same type of diode and they will both have the same thermal coefficient. And the whole idea of that is the voltage drop across these will change with temperature a little bit, but they don't want that to happen, so they isolate them with a piece of foam, which is probably deteriorated by now. And these can be replaced with just a regular like 1N4148 diode or something like that. The whole idea is you just want them to hold steady. And then this circuit right in here, these comprised of these 2 fixed resistors and this pot. So you have a 560 ohm, a 470 ohm, and then a 100 ohm. And the whole idea of this combination, this way that it is to be able to set the midpoint so that when you set this pot somewhere around in the middle, it should give you a midpoint output of 0 volts. And contrary to what it may say in the service manual, there is a typo in one of the service manuals. It says something about that you should set this to 80 millivolts of offset. That is not correct. You can see in the schematic even they're saying it's 0.02 volts. So essentially what they're saying is they want it to be 0 volts of offset at the midpoint here. And that's what this pot does. So you're just going to adjust this until you have your 0 volts here. Now, you have your input coming in from your input jack. This is where you connect your preamp. And this is a single-ended amplifier right here. And this is a constant current source. So this is your tail resistor with a current source on it. And that helps get rid of any kind of common mode rejection. And then you have your differential pair, which is the other input, which is your negative feedback. So the whole idea is we drive this. This is going to go into your pre-driver, which is a differential pair. And the reason they're doing that is they're taking one off of here, they're taking the other one off of here, which is your negative feedback. This sets the amount of feedback that you're going to have. So it's taking a little bit of the feedback and basically going to have an inverted version of what's up here going here. So this is going to cause this section right here to seesaw up and down along with what's going on at the input here. This is a current mirror. So essentially, this ensures that both of these sides will always have a matched current going through them. Why would you want to do that? Well, if you have changing current, what's going to happen is it's going to change the voltage drop. If the voltage drop and the current both change together, which they will if you have a fixed resistance, it's going to cause extra power to be dissipated on one side or the other. This ensures that it's a voltage amplification only. So this is a voltage stage, not a current stage. So that's what this current mirror does. And if you look the way it works, you have one side that's wired as a diode. You notice the collector and base are tied together. So essentially all you have is a diode. So you're going to have a diode facing this direction through here. This base comes off of here and it picks off that voltage and it's going to mirror the current that it sees on this side, hence the name current mirror. Now, these diodes should look familiar to most of you who work on this stuff. This is your bias spreader. So this is what's going to determine the amount of overlap you're going to have between these two transistors. But really, that doesn't matter a whole lot in this because this thing is running in class A, and we're going to talk about that in a second here. And this is what sets the idle current and so forth for the drivers, which is in turn going to set the idle current of the outputs. Now, this is a single-ended push-pull circuit, and it's very confusing because you see a complementary pair of transistors. You see an NPN and a PNP, and the same thing on the output, NPN and PNP. But if you look in the service manual, they refer to this whole section as a SEP, or single-ended push-pull, instead of a quasi-complementary or complementary output. And part of that has to do with the way that this thing is biased as class A. So in other words, you see how in red this is circled up here? It says 1.7 amps. Remember how hot this heatsink was getting? It is because there is 1.7 amps of current flowing between the positive and negative 28 volt rails. So you have a difference here of 56 volts, right? 28, a positive 28 plus a negative 28 is a difference of 56. So 56 volts 1.7 amps, you do the math, how many, how many watts of dissipation that is. And then what's happening is, if you look at the service manual, they're telling you that they want about 800, 850 or 820 milliamps of current flowing through one of these resistors here. And if you notice, there's two of them paralleled up. So parallel circuit, you have a current divider here. If you add those two 850 milliamp currents, you come to a total of 1.7 amps. And so there's a minimal amount of current here, almost none. It's very, very, very low because you're just driving the base of this. But most of the current is up here. And that is the reason it is in Class A. In other words, these transistors are turned on to their midpoint swing. So in other words, they're halfway to being all the way turned on, all of them at the same time. So what's going to happen is none of these transistors are ever going to turn off throughout the entire cycle of the signal that you put in here. So if you put a sine wave in here, as you go positive, okay, both of these transistors are turned on. As you go positive, these ones are going to turn on harder and harder. They're already halfway fully biased on. They're going to get really close to the rail at maximum power, we're talking. This will drop in current, but it won't drop to the point where it shuts off like it would in a Class AB. It will stay biased on throughout the entire process until finally this starts swinging negative. As this starts going more negative and the current starts going down up here, current here is going to start increasing again at the same amount. But you're never going to see this side turn off either. So neither side ever turns off. That's the whole point of Class A. And the train of thought with that is that if the amplifier stays in Class A, if these transistors never turn off, you will never hear any switching noise of this one turning off while this one is fully turning on. In a Class AB, that's exactly what happens, is after you get, a few milliamps of current extra flowing through one side, it'll eventually just, on this side, the other side will just drop out. It'll shut off because there's only a few milliamps of current at idle. So that's why this is Class A. And as such, you don't really have a phase inverter in here. In other words, you never really have to drive this thing in a negative phase. This whole circuit is kind of sitting at the midpoint. So this is a single-ended. Even though you have a positive and negative voltage, it makes you think this is a complementary amplifier. It's not. It's looking at this positive to negative as a single rail power supply. And this whole center part here, which is tagged into this center part here, is just sitting in its midpoint, and it's going up and down inside here. And the output is doing the same thing. It's never really going negative, if that makes sense. It's just going more positive or less positive. It's confusing. You have to really get your mind wrapped around how this works. But that's what this is. It all has to do with how this thing is being biased by all this. You could reconfigure this and keep everything pretty much the same and just turn the idle current way down on this, and the amp will switch into Class AB. You'll get a lot more output power, and you will also get a lot less heat, but you'll have that switching noise in there. Now, here's the thing. How many of you have listened to, a Pioneer SX980 or an SX780 or something like that, or a 750 or a 950? Those are all Class AB amplifiers. Do you hear any switching noise in those? I can't. But again, we're talking about little tiny nuances here. You really have to have a good listening environment, a good ear, and a good set of speakers to be able to really hear this. The other thing is, just to my ears, and again, this is anecdotal. I don't really know, I can't really say definitively how, but the amplifier has it seems to have a lot more punch at lower volumes. This one does, than a lot of the Class ABs out there. Although I've heard Class ABs that had a lot of punch to them also. So again, this really has to do with, critical listening, if you're into that. And that's the whole purpose why they're going through all this. It's super inefficient. You're wasting so much power. As we did our little experiment, you notice this thing is drawing full current from the mains at idle, and it never changes. No matter how loud or quiet you turn the volume, it pretty much keeps the same current draw out of the wall all the time at your mains voltage. So real interesting how this works. It's super inefficient though. It's like those old gas guzzler cars, from the 1970s. They put out 180 horsepower and got about 12 miles to the gallon, and now we have engines that are 300 horsepower and they're getting 25 miles to the gallon or 30 miles to the gallon. So big difference. So anyway, that's how this thing works, and it'll be really interesting to put this through all of its tests after we recap it and clean it and get it all ready to go. So just a quick overview of how this amplifier works. Now just a couple more thoughts on this before closing. Unlike a Class AB, these power transformers have to be able to deliver a lot of current constantly. Whereas with a Class AB amplifier, most of the time it's just sitting there delivering very low amounts of current. And unless you're really running the amp at really high volumes, it's not drawing much current from the transformers. So a lot of times manufacturers will cheat a little bit. They'll use a little bit undersized power supply because they can get away with it. They know that the only time you need full current is for impulse power, when you're driving the amp with those big instantaneous bass passages and things, the big transients. And as such, when you have a Class A amp, you really can't scrimp on the power supply. You have to have a really solid transformer. You have to have really heavy, rectifiers and so forth. Hence, these gigantic capacitors and these gigantic transformers here for just a 30-watt amp. That's why. So that's another reason that a lot of people, I think, believe that the Class A amps sound better. I don't necessarily know that it's the Class A part, but it's just because how overbuilt the amp has to be to run in Class A. I think that if you have a Class AB amplifier that's built to the same, toughness or whatever, it would perform very similarly, sound-wise. So that's another thought on that. Another thing is, I really love how Pioneer designed this without any special components. These are not special matched components. These transistors are standard output. They're 70-watt TO3 transistors. They're not, the ring emitter or LAPT designed transistors. They're just standard silicon transistors. Nothing is special matched other than these are matched because it's a package, and it really, there's nothing special about it, and that's really cool because it's a great design and it uses pretty standard components, and these are still very, very obtainable, and there's really nothing in this amp that you can't replace. You can't find some substitute that'll work. So another really good thing about this. So anyhow, those last couple thoughts. Now another interesting design feature that I saw and that I noticed in here is this 100 ohm resistor, this R34. It's 100 ohms at 5 watts. And if you look up here, this is where it goes out to your speaker terminals. And down here goes to ground. So basically, right after the, this snubber network coil, which notice this does not have a resistor in parallel with it. A lot of times you'll see a resistor in parallel with this coil at the output. But now they have the resistor going to ground, and it's in series and it's going to ground here, which is kind of strange. So what that means is when you connect your speaker here, you're basically putting your 8 ohm speaker in parallel with a 100 ohm resistor. Now my guess is they put this in there for stability. I don't know. And if you do the math, you're talking, if you put full power out here, and let's just say you're somewhere around that, 15, 16 volts or something like that, you're probably going to be dissipating about 2.5 watts into this 5 watt resistor. So this thing is going to get really toasty. So this might be something we may want to upgrade to maybe a 10 watt resistor to keep it from running so hot. I've never really seen anything like this before. I'm sure there's other designs or other amps out there that have this. But again, you're putting a 100 ohm resistor in parallel with whatever speaker you're connecting to it. So if you have an 8 ohm speaker, your 8 ohm speaker is now, dividing with this in parallel. So essentially that load to the amplifier is going to be a little bit less than 8 ohms. It's going to be 7 point something. So again, no big deal, but this must, like I said, maybe this amp had a problem with oscillation or something, and we're going to go through and do a couple tests just to see, as it is right now. Without having worked on it. I have a feeling this amp's going to be pretty stable. But anyway, I just thought that was interesting that that was in there. Now last of all, you see these couple wires that are kind of running off the page. I cut that off, but essentially these 130 ohm resistors here, not the emitter resistors, but these 130 ohm resistors, they're going out. You have these 2 test points. And then you also have, this goes out to your protect circuit. And that's with your overcurrent sense and so forth like that. That's all derived from those lines there, right off of the outputs. You can see that. And when they talk about where we're actually measuring for your idle current, that's what you're looking at, is the amount of current flowing through this 1/2 ohm 5 watt resistor, or these emitter resistors. So let's finish out the video by connecting this thing up. Let's put some speakers on it, or not speakers, let's put a dummy load on it and hook up the scope and the distortion meter and so forth. And let's just see what kind of performance this thing has, and what the distortion looks like, and a couple things. And again, this is an untouched amplifier. This is just how it came onto the bench. Haven't taken it apart, haven't even looked inside yet. We're just going to test it. Okay, before we finish out this part 1, we have to do a quick test, of course. And let me see if I can get lighting, which I can't get lighting because, lighting is a pain. Here, let's see. Does that get rid of the glare? That gets rid of the glare. Okay, here we go. So we'll let this thing settle. And we're looking at about 19 volts RMS. We're looking at 0.05% THD. And we have a nice clean waveform. Now 19 volts, that's like 45 watts. So let's drop that a little bit. Let's take it to, let me turn this off. Let's take this to about 15.5 volts, which is going to be right after this slash right here. So turn this on. I'm going to take it all the way down to 15.5 volts. Right about there. That is exactly 30 watts. And look at the THD. That's about as low as my meter will go before it starts getting into the unpredictable territory. So there's 30 watts, and you can see how clean this amplifier is. It's unreal. So at 45 watts, which was 50% over its maximum power rating, it was still only doing 0.06 to 0.07% THD with a really nice looking waveform. So I'm pretty happy with that. Beautiful. Okay, so the next thing we're going to do is the sweep test. And the whole idea is we want our power meter up here, we want this voltmeter to not move during the entire thing. We don't want this, as I said, breathing. So we want this waveform to stay same amplitude throughout the whole frequency spectrum. So we're starting at 10 hertz and we're going up to 20 kilohertz. And let's bring this down just a little bit. And let's start it up. And again, we're doing a power sweep at the full 30 watts per channel. And let me turn this up a little bit. And you can see it doesn't vary at all. It is absolutely rock solid. Now ignore the THD meter because of course it can't keep up with the frequency change, so it's not going to work. But up here, this is not even budging. I mean, not even the tiniest little bit as we go through the frequency sweep. It's very, very, very little, not at all really, not moving. So it's a very linear amplifier and a very clean amplifier. So we'll turn the sweep back off. And there we go, straight back down to 0.009%. Wow. Okay, focusing on the scope, we're going to take a 0.47 microfarad film capacitor and we're going to go to a square wave, and then I'm going to introduce that across the speaker load and see what we get. Not bad. Look, it really damps that ringing down immediately. See that? Perfect. And let's go over to the other channel. See what it does. Same reaction. So, very stable amplifier. Okay, well, that's it for this part. I think I'm kind of at a standstill until I can get the parts in. And it looks like it's going to probably be 3 or 4 days before I have them. This is, however, a holiday weekend out here, so I might have some free time at the bench. So I might do another small video, something that's like a single take video or something like that. And if you have any suggestions that you would like me to do in the meantime, feel free to share them down in the comments section. And if I have some time, maybe I'll address something like that. I don't know if you want to do maybe a little solder and chat, or maybe a how-to video, or some kind of other information, question and answer. I don't know. Let me know. Anyway, until next time, you know what I'm going to say. I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again real soon. Take care, everybody. Bye-bye.